Okay. All right.
So if I write here.
Yes, we can. Perfect.
Perfect.
Okay, let's get started. So our second speaker today is Franco Rota from the University of Glasgow, who's going to talk about exceptional collections and pseudolattices in mirror symmetry. Please take it away.
Thank you. Yeah, thank you everyone for being here, and thanks for this invitation. Yeah, I must confess my background is probably much less categorical than that of many people here, but I'll tell you a little bit about the stuff I do and why I'm coming to become more and more interested in some categorical aspects. So my main motivation in all of this is mirror symmetry, and I'll start by telling you a little bit of the story of this topic. I'll say something in mirror symmetry. This starts from an observation which was made concrete the first time in the 90s. If I start with what I call the Calabi-Yau threefold, for the less geometrically inclined, whenever I say this word, you should think about something like a flat space. So that's a flatness condition. Physicists have been able to associate to one of these things what's called a superconformal field theory. I will not tell you much about what these things are. I'm not the good person to say that myself. But you get a physical theory associated to a Calabi-Yau threefold. As a matter of fact, you can do that in two different ways. So I'll just make up this notation for now. To my Calabi-Yau X, I can associate what I call the A side and the B side, which are two distinguished ways of studying superconformal field theories associated to it. Roughly speaking, whenever I use the letter A, that stands for symplectic, as you could not have guessed. So yeah, the symplectic side gives rise to what I call the A side, and the complex geometry of X will give rise to what I will be calling the B side. So this observation that was done in the 90s by a team of mathematicians and physicists. This is a paper from 91 by Candelas, De La Ossa, Green, and Plesser. Is that they construct not one but a pair of Calabi-Yau threefolds, X and Y Calabi-Yaus, such that what I'm about to write up here happens. If I take the A side of X, then that's equivalent in some sense to the B side of Y. And likewise, the complex geometry of X recovers the symplectic geometry of Y. So these two Calabi-Yaus that accomplish something like this are usually called the mirror pair. And since then, a lot of thought has been spent on making these isomorphism precise, but also reflecting on how to construct mirror pairs given only one of the two sides. So this is a very long and complicated story, but I will focus on one conjecture which was made a few years after this beginning of the story, which is what's called homological mirror symmetry. I'll abbreviate mirror symmetry for MS. This was formulated by Kontsevich. So the first few instances of mirror symmetry were involving enumerative invariants. They were formulated using curve counts on X and Y. But this version of mirror symmetry just predicts that what actually is encoded into the mirror symmetry relation is an equivalence of category. So the content of this conjecture is that mirror symmetry is encoded in equivalences of categories. And I'll tell you a little bit about which categories encode this sort of data, and a little bit about how to extract it. So the category that is associated with the A side is what's called the Fukaya category. And the conjecture says that if I have a mirror pair, this Fukaya category, I'll tell you a little bit more about it in a second, should be equivalent to the derived category of coherent sheaves over the B side. So I have these two manifolds. I regard one as a symplectic manifold, and I extract data which I package in this category here, the Fukaya. And then on the other side, I regard its mirror as an algebraic variety. I look at coherent sheaves, and I take the triangulated category, which comes out of taking the derived category of its coherent sheaves. Okay, let me give you a couple of features of what these categories look like. The one on this side is what's called an A-infinity category, so arguably not category. The way this works is that my objects are Lagrangian subvarieties. Remember that this side here is what I called A side. So that's all symplectic. And on this side, I'm on B side. So I'll use complex geometry instead. So yeah, the objects in the Fukaya category are subvarieties of my categories that behave well with respect to the symplectic form. That's what the Lagrangian means. There's additional structures here that I will not tell you much about because it's a bit outside the scope of what I want to say. Morphisms in this category are governed by intersection theory. Between these different subvarieties, and the composition law is instead governed by curve counts. I should probably say disk counts. I have this tendency of saying that a disk is one-dimensional because I tend to work with complex things. In which sense, well, a typical composition of morphisms in this category, and maybe I'll say a little bit more if I have time left at the end, will look something like this. I'll have Lagrangian subcategories at 0 and at 1. The generators of the Hom spaces between them, and maybe with this category L2, are going to be the intersection points. P0 and P1 is P2. And typically the composition category, the composition law will look something like this. If I compose P0 with P1, that's going to be a scalar multiple of P2, where this scalar multiple is the area of this triangle in here, or that delta maybe. The symplectic area of delta. And so how many disks I can fit into a triangle like this will affect this composition law on this side. Okay. I am maybe wrongly assuming that people are more familiar with the category appearing on the B side. So I'll say a little bit less about those. But really this is a triangulated category that comes out of the abelian category of coherent sheaves. And really what I mean here is that since it's derived in this way, it naturally comes with a DG enhancement. So I think of this as a DG category, where the objects are complexes of sheaves, and the maps are maps of complexes. Modulo quasi-isomorphism, so we localize the class of quasi-isomorphisms. The composition is just composition of these maps. Yeah. Okay, so these are the two main categories that play a role in our mirror symmetry game. This story so far is quite general, but I'll now specialize to draw that. Scroll the screen. I'll now specialize to a setting which is slightly different from what I started, which is the positive curvature setting. And a version of what's above is still true, but somehow we can put ourselves in a somewhat nicer situation in which we can describe these two categories a little bit better. If you're more geometrically inclined, when I say positive curvature, I mean that the B side, I want it to be Fano instead of Calabi-Yau. So, yeah. And maybe the main references for this sort of work, that what I'm about to tell you, come from work of Seidel and collaborators. He has excellent studies in this. Okay, so when I'm in this setting here, a mirror pair looks a little bit different than before. I no longer have a pair of Calabi-Yaus, but I have a Fano variety here on the B side. And the A side will be a symplectic variety equipped with a regular function on it, which is sometimes called the potential. And this whole setup here, the Y with the W, is often referred to as a Landau-Ginzburg model. Right? It's okay. So this doesn't need to mean much, except when I look at the categories that I would naturally associate to these pair of objects, a somewhat nice structure emerges. So I don't want to make any general statement, but the categories Fukaya associated to Y and W and DB co of a Fano variety tend to admit what's called an exceptional collection. I'll tell you in a second what this is. The upshot of, the place where I'm going with this is that if you have an exceptional collection, you get a better grasp on the category you're working with. So let me give you what I think is going to be the only definition in my talk. And I should probably point out that when I define these things, I should be slightly careful of whether I'm working in the A infinity or the triangulated setting. And just to help myself work in a place that I'm more familiar with, I'll restrict myself to the triangulated setting. Everything I'm going to say makes sense on the other side, modulo some tweaks, and which has to happen if we want to compare these categories. But this is just somehow easier to state. Okay, so if I have a triangulated category T related, an object in T is exceptional if somehow its endomorphism algebra is really nice. Since I'm triangulated, I have a suspension functor or a shift, and I can just look at endomorphisms of E with its shifts And I claim, I mean, for E to be exceptional, I just want scalar multiples of the identity when the index is 0 and nothing else. This K here is a fixed base field, which I like to be the complex numbers, but it's not strictly speaking necessary. Okay, so one exceptional object is somehow as simple as they come. And one exceptional collection is just a little bit more than a collection of exceptional objects. If I have an ordered collection, E1 through En, of exceptional objects, I'll call it exceptional. So this is an exceptional collection if all EIs are exceptional. And also, I have no maps whatsoever that go backwards in my collection. So EI to EJ, considering any shift, maybe let me change my letter, is 0 whenever I is bigger than J. The second condition in the A infinity case is called directed, which I figured I'd mention because it makes it very clear what I mean by this. There's maps that go this way, but no map the other way is allowed in any degree. Okay. Oops. Okay, why do we like these? Before I say that, there's one more word that I have to teach you. An exceptional collection is full if I'll just collectively denote it E with a bullet, E1 through En, generates the whole category T in the triangulated sense. So T is the smallest triangulated category containing all the exceptional objects. So the reason why we like collections of this sort is the following fact, which I find amazing. So I'll just dub it an amazing fact. In the presence of a full exceptional collection, so if E is full, then the triangulated category that admits E as a full exceptional collection is equivalent as the derived category of modules over the endomorphism algebra within the category of the direct sum of these objects EI. So in other words, this fact allows you to boil down categorical data to somehow algebraic data. I make it sound, I mean, if you say it like that, it doesn't sound like a big step, but this object here really is an algebra with generators and relations. So it's often a very good way to get a hold on the structure of the category that we wish to understand. So this fact here allows us somehow to go from categories to algebras. Which is somewhat of a simplification of our problem. If one wants to prove mirror symmetry, essentially, one possible approach is to just compute these categories on both sides and then further compute to show that you have found equivalent objects or equivalent categories. But that's usually challenging, even if you reduce yourself to asking about isomorphisms of algebras. That's still a very, very hard problem. But one can sort of soften it a little bit by looking at some necessary conditions that should be implied, well, they are implied by a correct homological mirror symmetry statement. And these become numerical and they become essentially linear algebra. And it's something that a computer can just check for you. So I'll describe a couple more features that appear within these categories and how to distill them into numerical criteria. Maybe I'll number them. This is my first, which comes from the Euler pairing. So suppose I'm given categories of a candidate mirror pair, then again, I'll state it in the triangulated setting, but you can do the same in the Fukaya side. I can look at their K-theory. So I look at the zeroth K-theory of the derived category of Free sheaves. This is by definition the free group generated by vector bundles over X. I'll just say objects of Free sheaves in X, and you mod out by relations that are given by the triangles. In other words, you're trivializing all extension classes, and you get a nice finitely generated, well, yeah, I'm getting ahead of myself. If you have a full exceptional collection, so if X admits a full exceptional collection, then its K-theory, its K-naught, rather, is a finally generated abelian group with bases free, finally generated free, with bases the classes of the exceptional objects. Okay, so far so good. Moreover, it admits a pairing. So the Euler pairing I'll denote it with a chi, contribute to the common symbol for Euler characteristics. If I take two classes of objects in K-naught, then this denotes the alternating sum of the dimension of the Hom spaces between them, where the signs vary with the shifts that I consider. This is I and Z. Properness has already made an appearance since this webinar, and this is another case. If my X is a proper algebraic variety, then this is going to be a sum where all but finally many summands are zero. So I have no convergence problems. And if I write the Gram matrix with respect to my bases given by E of the pairing chi is this is upper triangular and unimodular. This just follows by the definition of an exceptional collection, which is great. For example, it gives us a non-bilinear, a non-degenerate pairing on this free abelian group. I can do the same on the Fukaya side. And so homological mirror symmetry for X and Y comma W implies that if I look at the, we call the Grothendieck groups of X together with their other pairings, then I get an isometry with that of the Fukaya category of YW with its Euler pairing. And I should say that this isometry, this is the first time that the word in the title shows up, because these forms are non-symmetric. This goes a little bit outside of what people usually call lattice theory. A lattice is, at least commonly, it refers to a free finally generated abelian group with a symmetric pairing. In this case, we don't have a lattice, but we have what people call a pseudolattice. I still have non-degenerate unimodular forms, but they are not symmetric. Nonetheless, yeah, this is a very concrete multilinear algebra question that one can ask. If you are trying to find potential mirrors, you have a necessary condition, which you can just check. Essentially just computation. Your computer can do this for you. I'll briefly mention a second criterion, which is very similar in spirit. This also is distilling a property of these categories, which is what we usually call self-duality. So both sides A and B admit what's called the self-functor. Self-functor is just an end-of-functor of your category, such that when I pair two classes in K0, then this pairing, it does more than this, but this is what I care about in this setting. So I'm slightly cheating about the definition of a self-functor, but numerically at the level of Euler pairings, this is what it does. It allows you to, in some sense, symmetrize modulo paying the price of inserting this transformation here. And this is given on the B side, which is the complex geometry, by the canonical bundle. If you're more familiar with differential things, I think an operator that is maybe not this, but something very close is what's called the Hodge star. And on the A side, this is a monodromy operator of the fibration that is induced on Y by the function W. Again, if I'm given a full exceptional collection, then I can express S in the basis corresponding to the collection through just a matrix, which is the inverse times the transpose of M, the Gram matrix of the Euler pairing chi of chi. And so a weakening of the first numerical criterion, again, homological mirror symmetry, will imply that if I get a self-functor on the A side, will give rise to a similar matrix on the B side. And this is extremely useful if you want to rule out candidates and you're looking for new mirror constructions, because this is really fast and really easy to implement. Of course, maybe let me with a couple of things that are next steps in this sort of framework. an obvious question is, how hard is it to flip that arrow? And another question that maybe not so evident in here, but we have an isometry above and a similarity here. Can we give these very explicit interpretations? Can we write down explicit maps that mean something geometrically? And those are sort of the two directions that I'm trying to work with my collaborators for a specific class of singular surfaces that I'm happy to tell you more about in the question time. Sorry, I went a little over time. I hope that was not too bad. Thank you for your attention.
Right. Thank you very much for the fascinating talk. Okay, we still have time for some questions. If anybody has any, feel free to unmute yourself or to write in the chat or raise your hand.
Yeah, I wanted to ask, like, in my mind, having a full exceptional collection is very almost being rational as a final variety. But I may be completely wrong, so maybe you can shed some light on that.
No, you are correct. So the presence of exceptional collections is something that you don't have when you're not final. That's almost like a general fact. But you're right that if you want a full one, then that's very, very close to being rational. So I slightly lied a little bit. And maybe my positivity assumption is a bit stronger than I made it look in that in the talk. Does that make sense? It's conjecturally, it's almost the same, right? There's a conjecture by Orlov that says that if you have a full exceptional collections of line bundle, I think, then you are rational. Still a conjecture, meaning we don't know any counterexample. So you're right in thinking that these are almost rational varieties.
Oh, okay, thank you. I was also thinking that maybe other examples could be weighted projective spaces, but maybe I'm also wrong.
They could be, but let's see. So I'm more of a surface person than anything else. If you think about surfaces, how many of those are not rational? Are you actually getting out of the class of rational functions if you look at weighted projective planes?
I guess if there's a conjecture, no. But
yeah, exactly. I would like to believe that these are all birational to the plane somehow. They're all toric, right? Yes. Yeah. Weighted projective plane is weighted projective space is a toric variety, so it is rational.
okay.
Yeah.
Well, thank you.
Sure.
Okay, any more questions or comment? Ivan, is that a raised hand?
Yes, I have a question. I'm really not in the field, so I really, this is my ignorance, but I did not understand where the classical results ended and your contribution started. So could you tell us, like, what is that you did in this story and what is classical?
Right. It's true. I haven't stated results or theorems. So some of this work is in preparation, but essentially much that isn't about this numerical criteria was already laid out to us. And the criteria are not hard per se. I decided to, on purpose, not focus much on my work, but what I'm trying to do with my collaborator, Giulia, with Giatti. We have a class of singular surfaces. So these are singular. They're not final because the anti-canonical divisor is ample but not effective. And there exist mirror candidates which are surfaces equipped with a certain vibration. The reason why they're candidates is that they are mirror pairs in the Hodge theoretic sense, so in the enumerative sense, and we want to upgrade them to homological mirror symmetry. So we have these candidates that are somehow geometrically mirrors. We are working in a setting where the usual mirror constructions do not work, because that's what you lose when you don't have this effectivity, but we still have exceptional collections here, full exceptional collections. And if you're familiar with rationality problems, then you know that the existence of a full exceptional collection is something that is not hard to prove for this class of surfaces. These are called log del pezzo. However, an explicit description of these full exceptional collections, meaning that we compute all the Helm spaces between them, and this is not quite written down in our paper, but we also have the composition law, so we can describe the algebras, appears in one of my work with Gujatman. It's our paper in Ainfty-algebras. Yeah, so where we come in is that we have this class of candidates, and we are just approaching the whole computation numerically using computer algebra to actually check lots of necessary conditions before we start the work of actually upgrading to the categorical statements. That takes much more work a priori than just checking numerical conditions. So now, for now, we're just extracting this sort of lattice theoretic data from the candidate mirrors.
Right, there's still 1 or 2 minutes for questions. I think Antonio has a raised hand again.
Yeah, I was also wondering about like all these Grothendieck-ring ideas and K-theory. Is there any connection with the stability conditions?
Ooh, I wish there was. Let's see. I mean, this question had to come from you, right?
Sure.
No, it is a good question. We are still at a point in which very little is known, especially in this case that I'm studying with Julia. So the answer is there should be a connection with all these things. What one expects in general as a sort of heuristic is that when I take my B side, a complex variety, I can attach to it this stability manifold. So the space of stability conditions over the category of covariant sheaves of this variety. What should happen is that homological mirror symmetry, I made it look like it's a little bit easier than it actually is. The mirror to X is not a specific Y, but it's a whole family of Ys. So there's a moduli space here to which these pairs YW belong. And the heuristic of mirror symmetry should be, this is verified in very small cases, and by small I mean low dimensional, like this is verified for curves and not much more. The heuristic is that there is a map between these two objects, and this map should be, at least for regions of both of these spaces, the universal cover. So if this is going to make any sense, the expectation under homological mirror symmetry is that the stability manifold plays the role of the Teichmüller space of the mirror moduli space. This is very, very hand-wavy and very, very conjectural. And I think it's also expected to be false in the way that I said it, because there's some odd theoretic obstructions from this map to being surjective into the moduli space. Yeah, but that's sort of where stability conditions enter the picture.
Wow, very insightful. Thank you.
Sure.
Okay, let's thanks our speaker again.
Thank you.
So thank you for coming. And again, if people want to stay at the end, there's